In this video, we will practice verifying trig identities such as these. Along the way, we may use some of these Pythagorean identities. So make sure that you've either memorized these or you have the ability to generate a chart like this on a sheet of scratch paper. In addition to that, make sure you understand the following. Say if I have a fraction that involves a trig function. Let's say sine x. I need you to understand that I can move this trig function to the other side of the fraction anytime I want to, as long as I change it to the reciprocal trig function. So the reciprocal of sine is cosecant. So if I move sine up to the numerator, it will become cosecant. Okay? Similarly, let's say I had cosine up here in the numerator, and for whatever reason I wanted to bounce it down to the denominator. I can do that as long as I switch it to the reciprocal trig function, which would be secant. So keep that in mind. When you verify a trig identity, it's important to stick to one side of the equation and make it look like the other side without ever modifying the other side. So usually we will pick the more complicated looking side to work with. So I'm going to pick this side. Our most common technique is to write everything in terms of sine and cosine. So I see the tangent, and I can certainly write that as sine x over cosine x. So this would be times sine x plus cosine x. Okay, so I've got that. So I see that this would be sine squared x over cosine x plus cosine x. Okay, let's see what happens if we combine these together. So right now, this is like having cosine x over 1. So what I'm going to do is I'm going to multiply by cosine over cosine, like this. Cosine x over cosine x. So that's going to give me sine squared x over cosine x plus cosine squared x over cosine x. All right, the point of that was just to get like denominators so I can add these fractions together. So now this would be sine squared x plus cosine squared x over cosine x. So I told you that we might need these Pythagorean identities. This is the most common one. Sine squared plus cosine squared equals 1. So here's sine squared plus cosine squared, so that's going to equal 1. So this becomes 1 over cosine x, which is the definition of secant x. And I believe that was the target. All right, so that's it. We verified number 56. Let's try number 57. I'm going to work the right-hand side, which looks much more complicated. And I'm going to use my normal strategy of trying to rewrite everything in terms of sine and cosine and see what that will do for me. Okay, so looking at the numerator here, I see cosecant, which is 1 over sine, and that's times cosine, which I'll just write cosine over 1 for now. And in the denominator here, I see that tangent, so that's sine x over cosine x. And then I see the cotangent, so that's going to be cosine over sine. Okay. So I'm going to combine the fractions into one fraction. So in the numerator, I simply have cosine x over sine x. Now in the denominator, I'm going to need like denominators. So I'm going to have to multiply this side by sine x over sine x. And I'm going to have to multiply this side by cosine x over cosine x. Okay, that will make a like denominator of sine x cosine x. So I can see that this is going to make sine squared plus cosine squared over the common denominator. So I've got sine squared x plus cosine squared x over the common denominator of sine x cosine x. So see that sine squared plus cosine squared? There's that Pythagorean identity again. Sine squared plus cosine squared is equal to 1. So this will now become cosine x over sine x. All right, that's that same numerator right there. But in the denominator, I now have 1 over sine cosine. Okay, well, when you have a fraction divided by a fraction, you can multiply by the reciprocal. So that's going to give me cosine x over sine x times, now I'm just going to do the reciprocal of this, which will be sine x cosine x over 1. Don't really have to write the 1, but why not? And then you'll notice that these sine x's cancel each other out. So that leaves me with cosine squared x. Now it's time to look back and see what the target was. Oh, look, cosine squared x, exactly what I wanted. So that problem worked out very nicely. Number 58, I will once again use my number 1 strategy of rewriting everything in terms of sine and cosine. And I notice that the right-hand side is more complex, so I'm going to start with that. Cosecant is the reciprocal of sine. So this would be 1 over sine squared. And then I've got tangent, which is sine over cosine. So that's sine squared over cosine squared. And then I have minus 1. I guess I'll leave that alone for now. Now I notice that the sine squared will cancel out. So far that leaves me with 1 over cosine squared minus 1. Okay, now I'm tempted to rewrite this as like cosine over cosine or something like that, but I'm remembering my Pythagorean identities, and I'm thinking of these ones down here. Keeping in mind that my target is tangent, I see this identity right here. Tangent squared is equal to secant squared minus 1. And then I notice that 1 over cosine squared is secant squared. So I have secant squared minus 1. And as you just saw, secant squared minus 1 is equal to tangent squared. So I can go ahead and write tangent squared. And there you go. We are done. All right, number 59 looks pretty interesting to me. I'm going to try to work the right-hand side. I'm noticing the 1 minus sine x right here. And when I look at my chart of Pythagorean identities, I see 1 minus sine theta right here. So that makes me want to multiply by 1 plus sine theta so that it will make cosine squared. So I'm going to try multiplying by 1 plus sine and see what happens. So of course to do that I have to do it in the numerator and denominator. So I need to multiply by 1 plus sine x over 1 plus sine x. So in the denominator, of course, like I just mentioned, that will make cosine squared. So in the denominator, I have cosine squared x. Now in the numerator, I should go ahead and do the distributive property here and see what I get. So this will make cosine x plus cosine x sine x. Okay, so I have that. So looking at the target where I have these two separate terms, I'm going to go ahead and separate this out. I'm using the idea that if I have A plus B over C, that's the same thing as A over C plus B over C. So that's what I'm about to do right now. So this should be the same thing as cosine x over cosine squared x plus cosine x sine x over cosine squared x. Okay, now I have some cosines that are going to cancel out here, so this is going to leave me with 1 over cosine x. Alright, and these cosines will cancel out as well, so that will leave me with sine x over cosine x. But of course 1 over cosine is the same thing as secant, and sine over cosine is the same thing as tangent. And I believe this was the target. Let's just take a quick look back. Secant plus tangent, secant plus tangent, we got it. When I look at number 60, two strategies pop into my mind. As soon as I see 1 minus sine x, like the last problem, I'm thinking of this identity right here. So I see the 1 minus sine. If I were to multiply by 1 plus sine, that would give me cosine squared. So one strategy would be to take this and multiply by 1 plus sine over 1 plus sine. Alright, and so this will give me cosine squared, and if I multiply this out, double distribute, whatever you want to call it, I bet it's going to give me this. The other strategy would be to factor this. And if I wanted to work the left-hand side, I would factor this. I would convert cosine to 1 minus sine x times 1 plus sine x. And probably the 1 plus sine x would cancel out, and it would probably turn out to be this. So just keep in mind, I could have done it either way. I think I'm going to go ahead and do it this way and multiply by 1 plus sine x. So that's going to give me, in the denominator, like I said, I'm going to have cosine squared now. Alright, so that puts me halfway towards what I wanted. Now, in the numerator, I need to multiply a binomial times a binomial. So I need to do a sort of double distributive property. So I need to multiply everything by 1. So that's going to be I need to multiply everything by 3. So 3 times 1 is 3. And then 3 times sine x, so that's 3 sine x. Okay, now I need to multiply everything by sine x. Okay, so now I'm distributing the sine x. So sine x times 1, of course, will be sine x. And then sine x times sine x will be sine squared. We have some like terms here in the middle. That's going to be 4 sine x. And when I write the fraction again, I will write it in descending exponential order. So I'm going to take my sine squared and put that in the front. So there's my sine squared x. And then these combine to make 4 sine x. And then at the end, I will put the 3. And this is all over cosine squared x. And wouldn't you know, when I look back at the target, this is exactly what we wanted. All right, number 61 looks very interesting. I'm seeing this 1 minus sine x a lot, and so I'm just going to keep doing what I'm doing. So when I see this 1 minus sine, I know that if I multiply by 1 plus sine, that's going to give me cosine squared. So I really want to do that. So that's, again, in order to multiply by 1 plus sine, I have to do it in the numerator and the denominator. And I need to take my chances. So this is going to turn out to be, in the denominator here, I have cosine squared. In the numerator, I need to do a distributive property here. So that's going to give me cosine x plus sine x cosine x. Okay, and in the meantime, I still have this minus tangent, which I will go ahead and write as sine x over cosine x. So I definitely want to put these together and see what happens, but to do that I need like denominators. So that's why I'm going to multiply by cosine over cosine to make cosine squared the like denominator. So I will multiply by cosine over cosine. Okay, so you can see now that I will have like denominators. And so I'm going to go ahead and combine these into one giant fraction now. So first I have all of this. So I have cosine x plus sine x cosine x. And see this minus sign? Here it is. And then I have this numerator, which is sine x cosine x. And then I have the like denominator that we knew we would have, cosine squared. Now I'm looking to see, are there any like terms, and boy are there, because we have a positive sine cosine and a negative sine cosine. So that conveniently cancels out. So that is going to leave me with cosine x over cosine squared x. So these cosines are going to cancel out. So that will leave me with 1 over cosine x, which of course is the definition of secant x, which I'm pretty sure was the target. And there you go. All right, let's try number 62. I'm going to try working the left-hand side, and I'm going to go ahead and try just rewriting everything in terms of sine and cosine, and then just see what happens. So tangent squared is definitely going to be sine squared over cosine squared. So here I have sine squared over cosine squared. I'm just going to leave the 1 for now. Tangent is sine over cosine. And then secant is 1 over cosine. Okay, so I'm seeing that I can put these two fractions together. So now I'm going to have sine squared over cosine squared plus 1 plus sine over cosine squared. All right, so I see that I have like denominators forming. I see cosine squared and cosine squared. So now would be a good time to replace 1 with cosine squared over cosine squared. So I will have like denominators. All right, I love how we can always replace 1 with anything over itself, including cosine squared over cosine squared. So now all 3 fractions have a like denominator, so I can go ahead and put these all together. So this is going to be sine squared plus cosine squared plus sine all over cosine squared. Now I'm noticing that I wanted a denominator of cosine squared, and I've got it. So all I need to do is simplify the numerator. Well, looking at the sine squared plus cosine squared, that is the most famous identity of the Pythagorean identities. That equals 1, all right? Sine squared plus cosine squared equals 1. So I'm just going to make that substitution, and then I have 1 plus sine x over cosine squared x, which, looking back at the target, is exactly what we wanted. So that is it for number 62. There is no problem 63, so that brings us to number 64. Now I'm noticing that we have something new on this problem, sine of 2x. That's going to lead us to another set of identities. Okay, these double angle identities. So sine of 2x is 2 sine x cosine x. Watch out for that. I'm going to try working the left-hand side. If I want to square this binomial, I need to multiply it by itself. So this is going to be sine x plus cosine x times sine x plus cosine x. So we're going to have to double distribute this. So if I distribute sine, that's going to make sine squared x plus sine x cosine x. And then if I distribute the cosine, that's going to make sine x cosine x plus cosine squared. Okay, now I see that I have some like terms right in this area. Sine x cosine x plus sine x cosine x. That's going to make 2 sine x cosine x once I put those together. So now I have sine squared x plus 2 sine x cosine x plus cosine squared x. Okay. So a couple of things are about to happen. So first of all, I'm going to go ahead and write the sine squared and cosine squared next to each other. Basically, I'm going to reverse these two terms. And you'll see why I'm doing that right away. So if I reverse these two terms, now I have sine squared x plus cosine squared x plus 2 sine x cosine x. Now this is a famous identity that comes up over and over again. Sine squared plus cosine squared is equal to 1. So I'm going to replace that with 1. In the meantime, like I just reminded you, sine 2x is equal to 2 sine x cosine x. So here I have 2 sine x cosine x, so that's going to be the same thing as sine 2x. And I look up and I see that that is exactly what the target was. So we have just verified this identity. All right, let's do one more identity. I'm going to work the right-hand side of this problem because it does look more complex. And I think I'll use my most common strategy of rewriting everything in terms of sine and cosine. So tangent squared is sine squared over cosine squared. So I've got sine squared over cosine squared. And then in the denominator, I've got 1 plus, and again, I've got sine squared over cosine squared. Okay? Now, I need to add these together, so I really need to have like denominators. So I'm going to replace the number 1 with cosine squared over cosine squared, so we will immediately have like denominators. Alright, so I can go ahead and just write cosine squared over cosine squared. And I'll do the same thing down here, cosine squared over cosine squared. So now I have these like denominators. So in the numerator, I now have cosine squared minus sine squared over cosine squared. And in the denominator, I have cosine squared plus sine squared over cosine squared. Now, both of these numerators are actually identities. Okay, I recognize this as an identity, and I recognize this as an identity. Cosine squared minus sine squared is a double angle identity. Cosine squared minus sine squared is cosine of 2x. So I can replace this numerator with cosine of 2x. So that's what I'm going to do. So now I'm going to have cosine 2x over cosine squared. Okay, over. Now this numerator has a value of 1. Sine squared plus cosine squared is equal to 1. So this is going to be 1 over cosine squared. Okay? Now, you can either multiply by the reciprocal, or you can just recognize that these cosines will cancel out. However you want to do it. I'll go ahead and do it the long way, just in case anybody needs me to, and multiply by the reciprocal, which is always how you divide a fraction by a fraction. So I have cosine 2x over cosine squared times cosine squared over 1. So notice that these cosine squares will cancel each other out, and that will leave me with cosine 2x. And I'm pretty sure that that was the target. Cosine 2x is what we were trying to get, so we are done. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.